A marble is dropped from the top of a 15-story building. The height of the marble above the ground in meters after t seconds is given by the formula h of t equals 44.1 minus 4.9 t squared. So here we have the graph. So at t equals 0, you can see that the height is, well, it's more than 40 meters. If we plug 0 in here, we get 44.1 minus 4.9 times 0 squared. Of course, this doesn't matter, so we get 44.1. So initially, that is at t equals 0, the height is 44.1 meters. This value here. And you can see that the marble is then dropped, and as time goes on, the height of the marble drops to 0. And you can see that at about 3 seconds, the height is actually 0. So when the height is 0, the marble is at the ground. If we want to find a time for which the height is 0, well, we put this formula equal to 0. So we get minus 4.9 t squared equals minus 44.1. So t squared is 44.1 divided by 4.9. That's actually 9, which means that t is the square root of 9, which is 3. So indeed, it does check out here. When at t equals 3 seconds, the height of the marble is 0. In other words, the marble has reached the ground. Now we are interested in the speed at which the marble hits the ground. The speed is the rate of change of distance traveled with respect to time. It's the distance traveled dh divided by the time taken dt. So h is the distance traveled here. Speed is always distance over time. Average speed, as you might know, is distance traveled divided by time taken. The dh refers to an infinitesimal amount of distance. dt is that infinitesimal amount of time taken to cover the distance dh. So it should be quite easy to remember what to do if you understand the definition of average speed. It's distance traveled over time taken. So it's dh dt. Well, that means the derivative of this function here. So we differentiate this function with respect to t. If we differentiate 44.1 with respect to t, we get 0. That's a constant. It doesn't involve t. If we differentiate this term, we multiply 2 by the power by what's in front. 2 times minus 4.9 is minus 9.8. Then we have t to the power of 2 minus 1. 2 minus 1 is 1. So this formula gives us the speed at any time. Geometrically, what does this mean? Well, if you go back to the idea of differentiation from first principles, you will know that the derivative of a function is the slope of a tangent to the function at t. So dh dt is the slope of this tangent to the graph of h at t. So the slope of this tangent is actually the same thing as the slope of the curve at this point. That's how we measure the slope of a curve at a point. We get the slope of the tangent to the curve at the point. Now we are interested in the speed at which the marble hits the ground. So this is the speed just before it hits the ground. Obviously when it hits the ground, the speed changes drastically. So you need to imagine the speed of the marble just before it hits the ground. At the instant before it hits the ground, its height, you could say, is 0. Well, it's slightly more than 0, but it's so small we can say its height is 0 at that instant. So the speed is the derivative of the distance with respect to time. The distance is h, worked out at t equals 3. Because at t equals 3, the marble actually hits the ground. We saw that earlier. At t equals 3, the height is 0. So we want dh dt at t equals 3. So we have minus 9.8 multiplied by 3. We get minus 29.4 meters per second. So the slope of this tangent is negative actually. So that tells us that the speed is actually negative. That's true if the object is falling down. See, upwards is positive in this graph. So if the object is falling down, then since its speed is actually has a negative sign, but we're not interested in the actual sign, we're just interested in the magnitude of this quantity. So the speed, we say, is 29.4 meters per second. We're not interested in the actual sign. The sign just indicates the direction of motion. If the object is moving in the direction of h, that's upwards, upwards is positive, then the speed will come out to be positive. But if the object is moving in the direction of decreasing h, then the speed comes out to be negative. Well, the velocity comes out to be negative, I should say. The speed is always a positive quantity. The speed is the magnitude of the velocity. More technically speaking, this is the velocity, v, and v has a direction, positive or negative in this case. Positive if the object is moving up, negative if it's moving down. But the speed is the magnitude of the velocity. The speed is always a positive quantity, it's a magnitude. As a matter of fact, we could nearly work out the slope of this tangent from the diagram. So this is just an aside. See, if we extend this tangent on, and then you will see that if we pick any point on the tangent and increase t by 1, then the change in y is, or the change in h, it's not y, it's h in this case, is the slope of the tangent. So the change in h would be this distance here. Well, it should be 29.4, it should be around 30, this distance, but of course, allowing for the accuracy of this drawing, this distance here would be the speed. You can see it's about 30. Well, it's a bit more than 30. Well, it should come out to be 29.4 if I drew it accurately enough. So this distance here would be the slope. If you pick any point on the line, increase x, or t in this case, by 1, and look at the change in y, that's the distance you have to go to meet the line. We construct a right angle triangle. That distance is the slope. If we are considering units, then the slope of this line is the vertical distance. The vertical distance is in meters, and the horizontal distance is in seconds. So this will be 1 second, and the vertical distance should be 29.4 meters. So you put the vertical distance over the horizontal distance. You put 29.4 meters over 1 second. Well, meters over second, seconds are written meters per second. So that's where the units come from. Well, it's just distance in meters divided by time in seconds. So the answer is in meters per second. H was originally given in meters, and t was given in seconds. In the second part, we want to convert the speed from meters per second to kilometers per hour. Well, to do that, we need to know how many meters are in a kilometer. Well, there's 1,000 meters in 1 kilometer, and to get 1 meter, we just divide 1 by 1,000, which is 0.001 kilometers. That's 1 meter. So 29.4 meters would be 29.4 multiplied by 0.001. And we need to convert seconds to hours. Well, we know that there are 60 seconds in a minute, 60 minutes in an hour. There are 3,600 seconds is 1 hour. So 1 second is 1 divided by 3,600, 1 over 3,600 of an hour. So we have 29.4 meters in 1 second. So we replace 1 second with 1 over 3,000, 3,600 of an hour. So how do we calculate this? Well, we're dividing by 1 over 3,600. That's equivalent to multiplying by 3,600. Or if you like, you could multiply above and below by 3,600. Multiply underneath, it's under this line by 3,600. It'll cancel the 3,600s. And then you have to multiply above by 3,600. So you need to multiply these three numbers together. That's what I've done here. You get 105.84, and your answer will come out to be kilometers over hours, kilometers per hour. The speed v of an object at time t is given by v equals 96 plus 40t minus 4t squared, where t is in seconds and v is in meters per second. At what times will the speed of the object be 96 meters per second? Now I have a graph of this function shown here. We want the times when the speed of the object is 96 meters per second. So we could go to 96 meters per second on the v-axis. Actually, this point here is 96, and read off the times. You can see one of the times is actually 0, and then we could go across here and read off the other time. The other time I think is 10, or it's very close to 10 anyway. It looks like 10 from this diagram. I'll have to work it out to confirm it. So at t equals 0, the speed is 96, and at t equals 10, the speed is 96. So it looks like what's happening is that at time 0 it has a certain speed. It's not starting from rest. And as time goes on, its speed increases actually. You can see as time goes on, the speed keeps on increasing. Now, by the way, the object could be moving in a straight line. The object itself is probably moving in a straight line. It's not necessarily moving in a curve. The object could be moving from left to right in a straight line. But at t equals 0, its speed is 96 meters per second. And as time goes on, you can see the speed increases, it reaches some maximum value. It looks like it reaches its maximum at t equals 5, its maximum speed, and then it starts to slow down. But of course the object is continuing to travel in a straight line. We could imagine it traveling to the right along this line here. It continues to slow down, and then at a certain time its speed is 0. See, at this time here, which looks like 12 seconds roughly, its speed is 0. So v is 96, so we put v equal to 96, and we have to solve for t. So we have 96 equals 96 plus 40t minus 4t squared. So we need to solve this equation for t. Now this is a quadratic equation. You can see that there's a t squared term, a t term, and a constant term. We get it into the standard form of a quadratic equation. What I will do is I'll flip this over. I will move the left hand side. I'll move the minus 4t squared to the left hand side. It becomes plus 4t squared. I'll move the plus 40t to the left hand side. Minus 40t. And we'll actually get 0 because these cancel out. We can subtract 96 from both sides, we get 0. I just wanted to make the t squared term positive. It's just a bit easier to work with. So you can see there's no constant term in this quadratic equation. We could use our formula, write down a, which is the coefficient of t squared, that's 4. Then b, the coefficient of t is minus 40. C, the constant term is actually 0 here. There's no constant term. And then what we could do is plug these numbers into the quadratic equation formula. However, since c is 0, it's a lot easier to solve this by factorizing. It's very easy to factorize a quadratic where c is 0 because we can just factorize t out of this, and we have t into 4t minus 40 equals 0. It's very easy to factorize it. We can pull t out of both of these. We don't have a constant term that doesn't contain t. We don't need two sets of brackets. We just need one set of brackets and take t out. The product of these two factors is 0. The only way we can get 0 is if either of them is 0. So it means that either t is 0 or the other factor, 4t minus 40 equals 0. And if we solve 4t minus 40 equals 0, we get t equals 40 divided by 4, which is 10. So we can see that at 0 seconds, the velocity is 96. It's easy to see actually if you put 0 in for t, these two terms disappear and we get v equals 96. It's easy to see it for t equals 0. But we also find that at t equals 10, as we saw in the diagram actually, the velocity is 96. So at 0 and at 10, the velocity is 96. In part 2, we want the acceleration of the object at t equals 2.5 seconds. So let's just see this on a diagram. 2.5 is about here. And if you can imagine going up to the diagram at t equals 2.5. Now, the acceleration is actually the rate of change of velocity, analogous to the speed being distance over time. Acceleration is velocity over time, dv dt. Okay, so speed is ds dt. The letter s is often used for distance, or it could be h. S is not speed, so it's distance over time for speed. Distance traveled divided by time taken. Acceleration is the change in velocity divided by the time taken for that change to occur. So obviously we're dealing with the acceleration at an instant. We're dealing with a change in velocity over a tiny interval in time, an infinitely small interval of time. It's velocity at an instant. So we want the derivative of this function. We want dv dt. Well, that's quite easy to calculate. If you differentiate 96 with respect to t, we get 0. Differentiate 40t with respect to t gives us 40. Differentiating minus 4t squared with respect to t gives us 2 by minus 4 is minus 8, t to the power 1. And geometrically, we should know that the derivative of a function is the slope of a tangent to the function. So the slope of this tangent is dv dt calculated at t equals 2.5. So this is dv dt, and dv dt is denoted by the letter a for acceleration. So we want the acceleration at 2.5 seconds, or dv dt at 2.5. Well, that's 40 minus 8 times 2.5. So 8 times 2.5 is 16 plus 4, which is 20. 40 minus 20 is 20. So the acceleration is 20. The units of acceleration are meters per second squared. So the slope of this line here should be 20. Okay, that means if you pick any point on it, say pick this point and increase t by 1, then the change in the velocity ought to be 20 meters per second. This distance here should be 20. Why are the units meters per second squared? Well, the units of velocity are meters per second. The units of time are seconds. Meters per second divided by seconds is actually meters divided by seconds squared, or meters per second squared. At what value of t will the acceleration become negative? Well, the acceleration is the slope of tangents to this graph here. So you can see for values of t ranging from 0 up to 5, the slopes of tangents to the curve are positive. See, the lines are going in this direction. See, in the last question we got a positive answer for the slope. We got plus 20. But look what happens at t equals 5. At t equals 5, the slope of the tangent, or the tangent, is horizontal, so the slope is 0. So this is the slope of the tangent, and at t equals 5, it's 0. Let's just check that. We want to see when the acceleration becomes 0 first of all. So if we solve this equation, find when the acceleration becomes 0, that at that instant the object stops speeding up or slowing down. At that instant the object is moving at constant speed. You know, if the acceleration is 0, the speed is constant. So we put the acceleration equal to 0, and we get t equals 40 divided by 8, which is 5. See, just what we have here. T equals 5, the slope of the tangent is 0. And from then on, for values of t that are greater than 5, what happens is the slopes of the tangents become negative. So the acceleration is negative then. So you could say at t equals 5 the acceleration is 0, but the split instant after 5 seconds the acceleration is negative. So when t is greater than 5, a is negative, a is less than 0. You just pick any number greater than 5, like 5.1, plug 5.1 in for t, this will work out to be negative. Or 5.01 or 5.0001 in for t will give you a negative value for a.